Hello, Introduction to Statistics. Topic of this video, probability. My name is Hadi Farhangi, and the content of the course, first, an introduction, then computing probability, then counting rules, and rules for computing probability. First, introduction. Probability is a value between 0 and 1 describing the likelihood of an event that may occur. This is the formula, and it can be between 0 and 1. When it is 0, probability is 0. That means there is no chance. For example, probability of Milky Way disappearing this year. No chance. Probability of 0.5, it is 50-50 chance. For example, probability of getting a tail when tossing a coin. Probability when it is equal to 1, there is high chance. For example, probability of raining in the Washington state this year. It is very likely. Experiment is a process that leads to the occurrences of observations. Outcome is a particular observation of an experiment. Event is a collection of one or more outcomes of an experiment. Some famous experiments are 1, tossing a coin, 2, taking a card from a deck of cards, and 3, rolling a dice. Tossing a coin, the picture is here, picking a card, rolling a dice, and these are famous experiments that you will hear about in statistics and probability very often. Example, tossing a coin is an experiment. After it is complete, one can observe what is the result. Another example, tossing a coin 2 times is an experiment. Assuming the letter H represents head and letter T represents tail, then the possible outcomes are H, H, HT, TH, and TT. Note that HH means 2 heads in a row, HT means first a head and then a tail, and so on. Another example, tossing a coin 2 times is an experiment. An event would be having 2 tails, which includes the outcomes TT. Another event would be having at least 1 tail, which includes the outcomes TH, HT, and TT. Mutually exclusive events. Events A and B are mutually exclusive if they cannot happen at the same time. For example, rolling a dice 1 time is an experiment. Event A is getting number 2 and event B is getting number 5. These are mutually exclusive events. In one roll of dice, we would either get 1, 2, 3, 4, 5, 6. They cannot happen at the same time. Independent events. Events A and B are independent if the occurrence of one event does not affect the occurrence of another. Here's an example, tossing a coin and rolling a dice. That's an experiment at the same time. If event A is getting a T tail in the coin toss and event B is getting number 4 in the dice roll, then these two events are independent because the occurrence of the T does not affect seeing the number 4 in the dice roll. Next, computing probability. Assuming the event is called A, then one should count the number of outcomes in the event A and call it NA. Also, one should calculate the number of outcomes in the experiment and call it NS. Then the probability of event A can be calculated as probability of A is equal NA over NS. This is the universal formula to calculate probability in a more fundamental case. Example, in 2003, the space shuttle Columbia exploded. This was the second disaster in 123 space missions for NASA. On the basis of this information, what is the probability of success in NASA space missions? So pause the video and do the calculation based on the formula that you saw. Event A is success, you can count it, and S is the entire experiment, 123, you can count how many, and then you can count probability. Here's the answer. Event A is the success in the missions, and A is the number of outcomes with success, which is 123 minus 221, and S is the total number of outcomes, which is 123. Probability will be NA over NS, 121 over 123, which is 0.9837, which is 98.37%. Another example, a gambler rolls a dice. What is the probability of getting a 6? Again, we have the event, which is getting a 6. We know total experiment, how many possible outcomes there is. We should be able to calculate probability. Pause the video and do the calculation. Here's the answer. Event A is getting number 6, and A is the total number of outcomes in the event, which is 1, and S is the total number of outcomes, which is 6. Probability of A is NA over NS, which is 1 over 6. Next topic, counting rules. To calculate probability, one needs to calculate NA and NS. Calculation of NA and NS may not always be easy. Here's a list of computing rules that help with the calculation of probability. These rules are 1, multiplication, 2, permutation, and 3, combination. Counting rule 1, multiplication. For the two events A and B, if the event A has n outcomes and event B has m outcomes, then total number of arrangements is n times m. Counting rule 2, permutation. The number of ways our objects are selected from n possible objects, while the order of selection matters is Pn n factorial over n minus r factorial. N number of objects, r number of selected objects, which should be less than equal to n. Another one is combination, which is slightly different than permutation. Counting rule 3, combination. The number of ways r objects are selected from n possible objects, while order of selection does not matter. Is Cn Rn factorial over r factorial n minus r factorial. N is the number of objects and r is the number of selected objects. So these three rules we use it for calculation of ns and na. Here's the example. I have 4 shirts and 5 suits. How many shirt, suits, outfits do I have? So we should be able to calculate this. Based on the multiplication rule, I have 4 times 5, which is 20 outfits. And how do I know I have to use first rule? Because I have total number of outcomes in one event, selecting a shirt, and another event, selecting a suit. In total, it will give me multiplication rule. Another example. There are 12 players on the SSU basketball team. The coach must pick 5 players among the 12 to play. Count the number of possible selections that we may see. So pause the video and see which of these counting rules is applicable here. Here's the answer. The order of selection here does not matter. This is the case of combination then, where n is 12 and r is equal to 5. Here's the total number of selections based on combination of 12, 5, which is 12 factorial over 5 factorial, 12 minus 5 factorial. And if you do the calculation, as you can see here, you will end up with the number 792. Another example. In the basketball team example, assume the order of pick will show the lineup of players. How many ways the selection can happen in this case. So pause the video and see what is the difference between this example and previous example and which counting rule will apply here. Okay, here's the answer. Because the order of selection matters here, this becomes the case of permutation, where n is 12 and r 5. Hence, the total number of selections is permutation of 12 and 5, 12 factorial over 12 minus 5 factorial, 12 factorial over 7 factorial, which you see the calculation here. And just be mindful that 7 factorials are being canceled here. In Google Sheets, to calculate permutation, one can use the command permute n and k. And to calculate combination, one can use command equal combin n and k. And here's in a screenshot of the Google Sheet where permutation and combination of 10 and 8 has been calculated. I put the number in the column C. When you see the permutation is much larger than combination. And of course, because that r factorial in C and R. Next topic, rules for computing probability. So assume previously, we saw some rules to calculate NS and NA. Now, if you know some probability, can this help to calculate some other probabilities? Given the counting rules in sections before, one may still have difficulty to calculate NA. Here are some more rules that help with calculating probabilities. These rules are 1, addition, 2, multiplication, 3, complement, and 4, conditions. Rule 1, addition. If A and B are two events that are not mutually exclusive, then probability of A or B is equal to probability of A plus probability of B minus probability A and B. This is the first one. So if it is easy to calculate probability of A, B, and B, then probability of A or B can be calculated using addition rule. Here's a Venn diagram of the events A and B. When we either have A or B, because of their overlap, we calculate probability of A, calculate probability of B, and because that overlap, A and B, has been counted twice, we have to subtract it once. Here's an example. What is the probability that a card chosen at random from a standard deck of cards will be either a king or a spade? Pause the video, think about it. Here you can say A is king, B is a spade. Now you want to calculate probability king or a spade. We can calculate probability of king, we can calculate probability of a spade, we can calculate probability of king and spade, which is a single card, king of a spade. Can I calculate probability of king or a spade? So pause the video and do the calculation. Here's the answer. Let's define event A as having a king, and A is equal to 4 since there are 4 kings, and S equals 52 since there are 52 cards. Probability of A is NA over NS, which is 4 over 52. Let's define event B as having a spade. NB is 13 since there are 13 spades, and NS 52. This means probability of B and B over NS, which is 13 over 52. Event A and B having a king of a spade, and A is 1 since there is 1 card. And this means probability of A and B is equal to 1 over 52. So probability of having a king A or having a spade B is probability of A or B is equal to probability of A plus probability of B minus probability of A and B. 4 over 52 plus 3 over 52 minus 1 over 52, 16 over 52, or 4 over 13, which is 0.3077. Rule 2, complement. Assume complement of event A is all the outcomes except the outcomes in event A. And the complement of event A is shown by tilde A. This rule shows the relation between probabilities of A and its complement. Probability of complement A is equal to 1 minus probability of A. Here's the example. The probability of raining in a particular day in the state of Washington is 40%. What is the probability of not raining on a particular day? Because I'm talking about not something is happening, this is the complement rule. So pause the video and see if you can calculate it. Okay, here's the answer. This not raining is the complement of raining. Then one can write probability of not raining is equal to 1 minus probability of raining. I have probability of raining, which is zero point 0.4. So 1 minus zero point 0.4 is equal to 0.6 or 60%. Rule number 3, multiplication rule for probabilities. For the two events A and B, probability of A and B is equal to probability of A times probability of B if A. If A and B are independent, then probability of A and B is equal to probability of A times probability of B. Here's the example. A golfer has 12 golf shirts in his closet. Suppose 9 of these shirts are white and others are blue. He gets dressed in the dark, so he just grabs a shirt and puts it on. He plays golf 2 days in a row and does not do the laundry. What is the likelihood both shirts selected are white? So pause the video and see which of the multiplication rules will apply here. Here's the answer. Event A, day 1, wearing a white shirt. Probability of A is 9/12. Event B, day 2, wearing a white shirt. This depends on the day 1, but one can calculate P/A, which is the probability of day 2 wearing a white shirt if the shirt on the first day was white. So probability B of A is 8/11. So everything subtracted 1. A and B, both days wearing a shirt. Since the 2 days are dependent, the probability of both days wearing a white shirt is probability of A and B is equal to probability of A, probability of B of A. 9/12, 8/11, which is 0.55 or 55%. And think about it. Why was probability of B over A wasn't 9/12? Because one shirt was worn before, so now 11 shirts are left. And PB of A, we assume the previous shirt was white, so now not 9 shirts are available. Instead, 9 minus 1, 8 shirts are available. So probability of B of A, B if A is 8/11, not 9/12. Another example, a survey by the American Automobile Association, AAA, revealed 60% of its members made airline reservation last year. 2 members are selected at random. Since the number of AAA members is very large, we can assume that the 2 members are independent. What is the probability that both made an airline reservation last year? So think about it. In the multiplication, should I use formula 1 or formula 2? The question is saying already they are independent. So pause the video and do the calculation on your own and see what you get. Here's the answer. Events A, member 1 made a reservation. So probability will be 0.6. Event B, member 2 made a reservation. Probability of B is 0.6. A and B both made a reservation. Since A and B are independent based on the question, one may write probability of A and B is equal to probability of A times probability of B. 0.6 times 0.6 is 0.36 or 36%. And the reference for this video was Lind, Marchal, and Wathen based on the book Basic of Statistics.